In this video, I'll demonstrate how to utilize Mood's median test for single case design research studies. The median test really isn't used very often anymore, but I think it fits well for this type of research design. I'll explain why, and I'll show you how to do it in SPSS. The percentage exceeding the median, or Pem, was introduced in 2006 by Sensing Ma, and there you have the reference for that study or paper in behavior modification. In Ma's article describing the Pem, there's no mention of any actual statistical test to fit the data. There's no significance testing. All that Ma described was how to do the Pem, and I explained that in my previous video. However, Parker and colleagues in a 2011 paper state that the most logical test to use here would be Mood's median test. And there's the reference for Parker et al., also in behavior modification. In addition to that, Morley's textbook, 2018, on single case design studies or designs, encourages people to use Mood's median test. And there's an illustration of how to do it in Morley's textbook, but without going into SPSS. So my goal here is to show you how to actually compute it. Alexander Mood, for whom the test is named after, was a stats professor at Iowa State in the mid-20th century. And while he was a professor there, he wrote a highly popular statistics textbook, first edition in 1950. Here's a cover of the second edition. It went into at least the third edition, probably more, I'm not sure. He joined the RAND Corporation and worked for the United States Air Force at Strategic Air Command, analyzing data, and reached the rank of Major General. Kind of an interesting career choice or path. The median test, it's simply a chi-square test, and it's designed to test whether several samples came from populations having the same median, according to Conover in Conover's classic text, Practical Non-Parametric Statistics. So really what we're doing here is we're looking at the baseline and treatment phase of a single case design study to see if the medians of those two groups of data come from the same population. Conover states that the median test assumes independent random samples. Every statistical test has different types of assumptions based on the probability distributions of the data that you're dealing with. And for the median test, it's not assumption-free. We have the assumption of independent random samples, and we're violating that in single case design research, despite the fact that Parker and Morley both advocate the use of Mood's median test. Doing so violates the assumptions here of the test itself. But I don't think that's going to be a big deal, and I'll explain why. The median test utilizes the chi-square test of independence, and if you know anything about the chi-square test, you're dealing with mutually exclusive categories that each data point can only fall into each box of the table that's produced, for example, a 2x2 classification table, and that all those different frequency counts are supposed to represent different people. And that's why we're violating it, because we only have one person in a single case design. So what the median test does in SPSS, if you enter the data directly, is it utilizes the grand median of all the data points in the database. Now, SPSS can do this. SPSS can do the median test. And when you have enough observations, it gives you the report as a chi-square. Otherwise, it uses Fisher's exact test. And for details on Fisher's exact test, you can see Sidney Sinkel's 1956 textbook on non-parametric statistics. So let's have a look at Fisher's exact test. Ronald Fisher, a little bit of history here, began working at the Rothamsted Experimental Station north of London in 1919. And the facility was originally the manor of the wealthy family, the Laws family. John Bennett Laws, after studying at Oxford University, decided to turn the family estate into an agricultural laboratory in 1834. Here's a photograph of the original manor, and there are newer buildings there. It's a functioning research facility today. The first experiments at Rothamsted began in 1843 with turnips, and this particular photograph is took it from the Rothamsted webpage. They have some visual history material there. It's really rather fascinating to read through. You can see that the crops are arrayed in different sections, and what they would do is they would apply different fertilizers to the different sections. Some would have pesticides and some would not. And in the history of Rothamsted, during a period of time in the 19th century, they would hire children to go through the fields and pick the bugs off of the crops. In 1922 or thereabouts, while having tea at the lab, Ronald Fisher, who's a giant in the formation of modern statistics, but at that time he was young and not really established, he offered to pour a cup of tea for Dr. Muriel Bristol, who is an algae and pesticide expert. Here's a photograph of her, and the credit there is for the Rothamsted archive. Joan Fisher Box, who was Ronald Fisher's daughter, related the story in her 1978 biography of her father, of Ronald. The cup in which Fisher offered to Bristol had the milk poured first, followed by the tea, and Bristol turned it down because she claimed that she could tell the difference as to whether the milk came first or the tea came first into the cup, and that she preferred to have the milk added after the tea had been poured. Now Fisher didn't really believe this, I think, based on the description anyway, and he decided to put it to the test. So he and a friend who was also there at the laboratory provided Bristol with 8 cups of tea, half of which had the milk first, half of which had the tea first, followed by the milk. And so Bristol's task was to determine whether the milk or the tea was placed into the cup first, and she apparently was able to correctly answer each of the 8 times. There's a nice description of all of this provided by Sen in the journal Significance, which is the journal of the Royal Statistical Society. That's available free online. You can just find that and read more about the tea tasting and the statistics involved. This is a table from Sen's article. And essentially what happened is that without any statistical means of which to test the probabilities here, Fisher set out to determine how could we find whether Bristol had an ability that exceeded chance, that exceeded guessing. So he created a 2x2 table, and he charted out the actual state of affairs, and then worked out the probability that this could have been achieved by guessing the results. And this became known as Fisher's exact test, essentially because he produced the exact probability of this event happening if there is no special ability to determine whether the tea or milk came first. It's a precursor to the chi-square. So let's apply it to some data. Here you have data provided by Lens. And I talk about this data set in one of my previous articles on the percentage of non-overlap data, or P&D. So what you do in order to get the the Moods median test in SPSS. First, you find well, you can enter the data directly, but if you don't have a raw data set and you want to use a 2x2 classification table, this is how you would do it. Find the grand median of all the data points. Add your horizontal line across from the y-axis. In this case, the median is 21, so we add the horizontal line at the value of 21 on the y-axis. And then, as you can see with the classification table that I produced down here, for the baseline, we have one data point that's below that median and 6 that are above, 1, 2, 3, 4, 5, 6. And you do the same thing with the treatment phase. Now, let's see, so 1, 2, 3, 4 above, here's the 4, and 1, 2, 3, 4, 5, 6, 7, 8, 9 below. If you use the raw data, SPSS will count the ties. I think it's more logical not to count the ties. And so producing the 2x2 classification table will give you a more accurate result than SPSS will if you use raw data. So you have to be able to enter the data using this approach in order to get the pattern that I'm going to show. So we tabulate the points above and below, enter it into our 2x2 table, and in SPSS what you need to do is create these variables. And I'll show you how to do that. Let me jump out of PowerPoint here. And so in your variable view in SPSS, we're going to create variables called time, and I'll call it cut score for the median, and then count. So then going back to data view, you can see that these are blank, and in order to fill them in, we need to give time and cut score values. So we go to the values option in variable view, and when you click that, I'll do that again. So once you highlight one of these fields, you get the pop-up box. And what I'm going to do is I'm going to call for the variable of time. I'm going to call it baseline and treatment. So 0 equals baseline. Add that. 1 equals treatment. Add that. And click OK. And do the same thing for cut score. 0, in this case, 0 equals below, and 1 equals above the median. Below median. Let's spell that correctly. Below median. And 1 equals above median. Now we go back to data view. We need 2 baselines, one for above the cut score and one for below the cut score. Now it should look like this. And I do the same thing for time, rather for treatment. I have 2 outcomes for treatment, one for above the median and one for below the median. Now I can enter my cut scores, or the, go back to PowerPoint, I'm going to enter these scores right here, the 6, 1, 4, and 9. Make sure that those match correctly. Baseline has 6 above the median, 1 below the median. Treatment has 4 above the median and 9 below the median. For this particular data set, for the lens data, our goal is to reduce the scores so a lower score shows an improvement. Now, in order to actually use this, what we have to do is follow this pathway. Go to Data, Weight Cases, click Count, which is our variable where the frequencies are shown, then click Weight Cases By and carry it over. Once you do this and click OK, nothing's going to happen, but SPSS will now know to use this count when it analyzes data. So you can see that the output doesn't do anything. But now we can set up a crosstabs. Go to Analyze, Descriptive Crosstabs. And what we're going to do is we're going to create a 2x2 table that matches the one shown in the PowerPoint. We're going to put time in columns and cut score in rows. I don't have to do anything with count because I already told it that it's using count as the frequency weighting system. Click the statistics option, ask for chi-square, click OK. And you can see the output here. This will give you the same thing as the Moods median test if you use the Fisher exact test right here. So 0.057. So it's sort of a shortcut cheating system. If you have the raw data, you can analyze it by going into non-parametrics, legacy, and K independent samples, and you can see the median test option right here. But I don't have the raw data set up here. Furthermore, if you use this pathway for the median test under non-parametrics, it will count those ties. So and I think it's logical not to use the ties. If your goal is to avoid using the ties, then you shouldn't use the raw data, but rather you should use the setup that I just illustrated, using the weighting system. You can see that there are two data points here that are tied, and if you use the raw data, you'll get a slightly different answer because it's going to count those two data points. So we take our output, and since we have fewer than 40 cells, or rather, since we have fewer than 40 observations or data points, and because some cells have less than 5, you should use the Fisher exact test. If you had more data points, and if you had all cells having greater than 5 observations, then you can use the chi-square value, but use the continuity correction for that. You can see that there's not much difference here between the continuity correction, which is the Yates correction, as compared to the Fisher exact test. They're almost the same. But really, the Fisher exact test is the one that we want to use because it's a more basic version of the chi-square. So there's our p-value. And what I'm going to do is I'm going to actually take this one step further. So this essentially is Moods median test without using those ties. But I'm going to take that p-value, and I know I'm violating an assumption here, but this approach is used by Robert Rosenthal in his meta-analytic work, where you can take a non-parametric statistic, convert it into a z-score by using the p-value. Any p-value calculator will do this for you. Just make sure that you're using the right number of tails. So for this particular p-value, we would have an equivalent z-score of 1.9, and then using the formula provided by Rosenthal, in order to turn this into an effect size R, we can convert it using 1.9 over the square root of the number of observations. Now this is supposed to, n is supposed to be the sample size. So I know I'm sort of cheating here a little bit, but I want to illustrate for you in this video that I think that this number is actually an accurate reflection of what we're doing. So this is the Pem Median Test. And Pem does not utilize those ties. That's why I think it's important to ignore the ties and set up SPSS on your own with the weighting system. So here's the data from Lens. The baseline median is 25. That's what makes this different than the Moods median test, which uses the grand median. Instead of the generalized median test, what I'm going to do is I'm going to use just the baseline phase. And that's more appropriate for baseline treatment, single case design studies. This is a better reflection, I think, of phase change from baseline to treatment. So we compare now the baseline median to the treatment phase. And now you can see that there's a different pattern. Of course, for the baseline, half of the observations are going to be above and half below because the median is based on the baseline section or phase. So by definition, it's going to have half above and half below. But the picture for the treatment phase is a lot different. And you can see that there are 2 data points above that baseline median, whereas we have 13 below. So we go through the process of analyzing it using the weighted system in SPSS, and Fisher's exact test comes out to be 0.115. The corresponding z-score, 1.576, is then turned into an effect size R of 0.344. And that would be a medium effect size. I think that that accurately reflects what is going on here. When we look at the data, it's a fairly pronounced trend, but there is some overlap with the baseline phase. So it's not until you get down here that you start to see the real difference. And I think that this effect size, this medium effect size of 0.344, is a fairly good representation of what's going on here. Of course, it doesn't show you the trend line, but the visual analysis does. So here's another data set, and this one shows a small difference between baseline and treatment. Using the same approach, I take the baseline data, calculate the median, enter my horizontal line at the median phase, at the median score on the y-axis, count the number of treatment phase data points above and below the line. In this case, unlike the previous one, higher scores are better. So higher scores are favorable. But it doesn't matter which direction. The median test is simply going, or Fisher's exact test, is simply going to tell you whether the pattern is achievable by chance or not. And in this case, we see that the p-value does not reach the traditional level of significance of 0.05. We convert the p-value into a z-score. That's the z equivalent for that p-value. And then we can transform the z into an effect size R. And it's relatively small, doesn't quite reach the medium threshold of 0.30. But it's not nothing. And you can see that there is a bit of a change here, although it's not statistically significant according to Fisher's exact test. And then for this variation, this was one where I created some fake data that I thought would show a pronounced change at treatment phase. And you can see that change reflected in the 2x2 classification table, with 12 of the treatment data points above that baseline median and 0 below it. And you can see that Fisher's exact test comes out to be statistically significant at the traditional 0.05 level. Convert that into a z-score, and then convert the z-score into an effect size R. And yeah, I know I'm violating some assumptions here, but my goal here is to really look at the patterns and see if the effect sizes make sense in relation to the data. So when we look at the benchmark standards for P&D, which was provided by Scruggs et al., 90% or above is highly effective, 70 to 90% moderately, and 50 to 70% questionable effects. The PND, which I calculated in one of my previous videos for these data sets, does not seem to really accurately reflect what's going on. The lens data shows a moderate change in treatment. And so, when you look at the small difference data set, medium difference data set, large difference data set, the patterns do not seem to be accurately reflected in the PND. If we look at the PEM, it does a better job. The percentage exceeding the median does a better job of reflecting the benchmarks here. And then if we use the Fisher exact test, you can see that the small difference data set does not reach significance. The lens data set, which shows a moderate increase at treatment phase, almost reaches statistical significance. And the large difference data set does reach statistical significance. So you might consider this to be a little bit conservative. I think it's apt to be conservative in situations like this because we're dealing with sample sizes of one. Multiple observations of a single individual should be viewed with caution. And so I think that the Fisher exact test is a good fit for this type of data precisely because I want to be conservative in judging whether or not the treatment caused a difference relative to baseline phase. So it's one thing to see the difference, but it's another thing to be relatively certain about it. And then converting these into effect size R, I have a lot of experience with this particular metric of effect size. And I think that these, on a subjective level, these make a lot of sense to me in terms of those data sets that were presented. So this is perhaps an area for more research, and I hope that this would prove useful to some people doing single case design research. Thanks for watching.